Um, so funny you ask. It promotes shared states, mutable data, and side effects. That's basically what Jupe is. It's everything that a functional programming is not. So when we talk about shared state, what we're talking about is, or it's also known as a state pattern. You can think of it as an object, having an object and it's at a certain state. But some of its behavior can change accordingly. Mutable data, so that's basically a changeable object. It's kind of similar to shared states. It can be modified after the object has been created. In JavaScript, you see it everywhere with like objects, arrays, pushing and popping, functions, classes are examples. And what do we mean by side effects? Side effects is any application state change that is observable outside of its function call. So, for example, if you're writing something, if you have a function that's writing to a screen or a file, or if it's logging onto a console, so basically it's triggering any external processes. So I'm going to just bring it back a little bit and kind of talk about what a JavaScript object is. And I know some of this is really basic, but I don't want to get too technical. But so basically what we have here is a JavaScript object. And here we have a person function. We're passing in these parameters, which contains, first name, last name, age, eye color. And then, we can write, we can set we can add a new person. Excuse me. We can add a new person by adding values to those properties. So, for example, we have John, first name, string, Doe, last name, et cetera, and that's how we could do it. So, what if I wanted to add like hair color? Well, then obviously we would have to go inside the person function and do this dot hair color equals hair color, or this dot height equals height, blah 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 blah, and that's not fun, especially if you're, I don't know, it could be very repetitive, and so with that being repetitive, this defeats, excuse me, the dry principle. So we don't want to repeat ourselves, obviously. Like, that's not how we should program, because JavaScript is a beautiful program that allows us to do better than that. That would make JavaScript really daunting. We had to continually repeat our code and keep adding properties in the same function. So this kind of goes into what is Jupe. So kind of what we talked about. It promotes shared states, mutable data, side effects, and it kind of relates to the 4 principles of object-oriented programming, which is abstraction, encapsulation, polymorphism, and inheritance. I'm not really going to go into that today because this is a lightning talk, and I don't know, but I would say I will talk a little bit about inheritance a little bit, but the other stuff, if you have questions about it, you could ask me later or look it up. So in order to kind of make JavaScript a little bit more programmer friendly, we have the prototype, who is the hero. So what that does is JavaScript objects inherit properties and methods from a prototype. And I will kind of show you what that means. So if you remember, if you think back about the slide with the functional programming and how we had to, how it's not really dry, it's not programmer friendly. So if you look at this function and you compare it to this function, so this function still has that person object, but now we're going to use and introduce prototypes. what's nice about prototype is, like, if you forgot to, you know, add something for a person, like height or weight, here I have shoes, you can add that after the object has been created. So, so it allows you to add new properties to object constructors. Which is nice. And I like to think it as keep it simple, stupid, but it's really just dry, don't repeat yourself. But anyway, whatever. So JavaScript prototype, it uses inheritance. And so you might not realize it, but you're implementing object-oriented principles with prototypes. And you're actually implementing inheritance. So JavaScript objects inherit properties and methods from prototypes. So for example, if you're using like date.prototype, or you can get certain, I guess, properties that way. And there is actually a higher order function. The object prototype is on top of everything else, or that gets executed first. And so here, now I'm going to talk about how shared state is happening. And right here we have a person object. And so again, shared state is any variable object or memory space that exists in a shared scope, or as a property of an object being passed between scopes. So this is a case of this is actually a case of a shared function. Excuse me. So this is actually sharing data sharing data between objects. So for instance, if we could think of a person as a human being, human beings is like the master object in this case, and we can think of a person object as having shared stored properties like name, height, weight, etc. And so with that in mind, so in order to get access to those, like to the property name, it's a prototype property. They share the function describe. So in order to get, let's say like Jane or Tarzan, they have a shared function. We just do describe dot Jane in order to get, or I'm sorry, describe dot name to get Jane, I believe. And that's pretty much it. So you can find me later for questions. You can find me on Twitter. I'm trying to be more active on it. And I'm also on LinkedIn.
So we'll just take a quick restroom break before we get started. There's still good.
And you know, now is probably about the time too.
Okay.
So yeah, we're super excited to kind of bring everything back in here. And welcome up our visiting speaker, Guy Royce from Data Robot. So I think we'll let you take it away.
Cool, thanks. Wow, applause. There's no way I'm living up to that expectation. So, welcome. How's everyone doing tonight? Good? Thank you for coming out on December 19th. It's the, the busy time of the year for meetups. It's the nature of December, everyone's busy doing other things. So, I actually made the mistake, this is totally unrelated to my talk, but of getting married in December, like 24 years ago. And so I, in addition to having Christmas and all the other stuff going on, I also have to plan an anniversary event. So, pro tip, if you're not married, don't do it in December. This talk is called Deep Learning Like a Viking, Building Convolutional Neural Networks with Keras. How many of you have heard of Keras before? I mean, before you saw the thing. It has absolutely nothing to do with JavaScript. But it does have to do with Vikings, and since, well, we're in the Twin Cities, that seemed like an appropriate topic. So, Well, it's mostly Python code. I will have some JavaScript code tonight, but a lot of the content is just around neural networks and specifically convolutional neural networks and how they work. And then I'll demo a thing that I built using Keras and Python. And it does have some JavaScript in it. And my name is Guy Royce. I'm a developer evangelist at Data Robot. And what it means to be a developer evangelist is I go out to meetups and give cool talks about things that I like and I get excited about. And I say, I work for Data Robot, you should check it out. And also mention that we're hiring. So if you're looking for work as a Python backend and React frontend, we're looking for people like that. I'm on Twitter. I'm at Guy Royce. The reality of it is if you Google the name Guy Royce, even if you spell my last name wrong, you will find me because I'm the only person on the planet that's still alive that has that name. So I'm not hard to find online. But yeah, follow me on Twitter. Tweet at me. I'll ignore it, but it'll be great. I've got my GitHub on there. All the code that I'm going to show you guys tonight is on my GitHub account. The slides are on GitHub as well as a PDF file. So it's all right there, and I'll have a link to that GitHub repository at the end of the presentation. So can anyone tell me what this stands for? Oh, sorry, that's in runes. Can anyone tell me what this stands for? Any guesses? I didn't bring any swag to bait people to guess with. Usually I bring t-shirts, but I shoved everything into a little suitcase because it's just I'm going back home tomorrow. This stands for I am not a data scientist. I'm not a data scientist by profession. I'm a developer. I've been writing applications for 25 years. In fact, I run the JavaScript user group in Columbus, Ohio, and I've been programming in JavaScript quite a bit. Python's relatively new to me, so I'm not like a seasoned Python pro. I've never built an app in Python of consequence, not like a proper production app. I've done a lot of Java in my career. I've done a lot of things over the years. I'm very much a developer, not a data scientist. I don't even have a very strong math background, but I've been learning how to use these tools for data science. Keras is one of them, and it turns out that that stuff's not essential for you to make use of it. So I'm going to show you how it works, get the principles in your head, and but I'm not a data scientist. So if you have really deep experience in this area, you probably know more than me. What I'm really doing is going around and I'm learning stuff, and then I'm putting together talks, and then I'm sharing with everyone. And so this is where I'm at the moment with regards to building convolutional neural networks. I have some other knowledge in here, but most of it's here in these slides. So. One of the reasons I didn't talk about Vikings is because I'm part Viking. As you can see, I went to the 23andMe and spit in the little test tube thing and found out that I'm actually 2% Scandinavian. So that's why I'm so interested in Vikings. I'm still 100% guy, though. Actually, I didn't do that, but I totally made up these numbers, but they seem plausible. I'm from Ohio. Everyone in Ohio has either got an English or German background, so not nearly everyone that's natively from there. I guess if you're English and German, you're not natively from there, are you? But regardless, yeah, so, you know. Actually, I just think Vikings are kind of cool. And they've got these runes, these Rune Stones. This one's a Rune Stone in Stockholm, outside of Stockholm. And you know, this particular Rune Stone, it's called a Rune Stone because it's a stone, and it's got runes on it. And runes are those little, if you guys can see, whoops, go back, is the writing on there. It's the alphabet that the Vikings used. How many of you have played Dungeons and Dragons? Okay, so you know what runes are, right? But this particular inscription's in Old Norse, and it's a memorial for a woman's fallen husband from her and her sons that they erected it, which is actually kind of sweet. But you can see the D&D on it, right? It's got the runes, and it's got the dragons, and it's got that like iron cross kind of thing at the top of it, and you know, it feels kind of epic, right? And so the runes were the letters that they used to write stuff in Old Norse with. And the alphabet that they used was called the Younger Futhark. And the Younger Futhark has 16 letters. The reason it's called Futhark is because F-U-T-H-A-R-K. So the first 6 letters of this alphabet spell the word Futhark. And I picked it because it was the thing the Vikings used, and I wanted to build a tool to do classification of these things. If you transliterate names into this, I took my name and did it phonetically. And I found that you kind of end up with good fantasy D&D character names this way, because there's no G in any of these letters. And so K is the next closest sound to G. And so I picked cow. I guess that's how you pronounce that. I don't know exactly how to pronounce that rune. And then ass, that's the name of the rune. It makes the A sound, so it's got to be pronounced ass, which is, go ahead and snicker like 12-year-olds. It's okay. So I did an AI combination to get the guy sound. So this is literally G-A-I, or K-A-I. So Kai, which is kind of like guy. And then there's no O either. So the Royce became Rice. So it's Kai Rice. That's my name in Old Norse. I feel like more of a badass already. You might notice when you look at these characters that some of them look familiar. Like if you look at Bjork in particular over there, it's the one that looks like a B. And the top line here, or the middle line here is the Latin letters where they're kind of similar. So if you look at Fe, looks kind of like an F. You can see how might have been a U, it's just been flipped upside down. Wreath is clearly an R. So there's lots of similarities here. And there's also similarities with Greek letters. So like soul it makes the S sound. And it looks like, an S, sort of. Looks like a stylized S. And it also looks kind of like a sigma in Greek. And these letters all related. And even the logger, which makes the L sound, kind of looks like a lambda. It looks more like a lambda than it looks like an L, actually. So it's interesting that these letters look the same. I know what you're all thinking right now. It's like, I thought he was going to talk about technology. I will. I just think this stuff's neat. So, well, there's a reason for that. And that's because this alphabet, this runic alphabet, is called the Younger Futhark. And so that suggests that there was an Elder Futhark, which earlier groups used. There were 24 characters in that. And we have our modern Latin alphabet here as well, that we are all familiar with, I hope. And that came from the Latin alphabet. And both of those came from Etruscan. Actually, the Elder Futhark may not have came from Etruscan, they're not sure. Etruscan was another tribe in Italy where Tuscany is today. And they had their own alphabet that they got from the Greeks. And the Greeks got them from the Proto-Canaanites. You might not know who the Proto-Canaanites are. The Canaanites were mentioned, of course, in the Old Testament. But they were also called the Phoenicians. That's what the Greeks called them. And so the Greeks got their letters from the Phoenicians. And actually, they ultimately got them from Egyptian hieroglyphics. And so the really cool thing here is that Egyptian hieroglyphics spawned all these alphabets. It actually spawned Aramaic, modern Hebrew, as well as ancient Hebrew. Even the alphabets used in India and stuff, they're all from hieroglyphics. Only in Far Eastern Asia do you get some exceptions, like Korean doesn't come from this, Japanese doesn't come from this. But anyhow, so they all have common ancestors, that's why they look similar. And that's really cool, but that's not why we're here. It's just kind of neat. We're here to build a convolutional neural network to recognize runes. So this is an image classification problem. I want to draw a thing, and I want the software to tell me what that thing is that I drew. And in this case, we're going to draw one of 16 runes, and it's going to say, you drew haggle. You're going to draw haggle, and it's going to say, you drew haggle, which is what that rune is there. It makes the H sound. And convolutional neural networks are how we're going to do it. But before I go into that, I want to talk a little bit about what neural networks are. So a neural network is it's a way of doing machine learning, and in this specific case, it's deep learning. And you probably heard the term deep learning, right? And you probably heard the term machine learning, and deep learning sounds cooler, right? Because it's deep, man, it's deep. Yeah, no, it's not actually. Deep learning is called deep learning because you've got these neural networks. And see here in the red, we've got an input layer, and in the yellow, we have our output layer. In this case, we have two outputs. And then we have these hidden layers between them of these neurons connected together. Math, numbers flow through them. And that hidden layer, if you have lots of them, your network is deep, as opposed to shallow. not deep as in profound. Right? It feels like it should mean profound because we've all seen those images that Google generated when they ran their networks backwards and it created all these acid trip type images of eyeballs everywhere and stuff. It's like, yeah, that's deep, man. You know, that's not what they meant. But I can see why someone would think that. But no, it just means deep as opposed to shallow. And in this case, this is actually a small example of a deep learning neural network. It's very, very small, and obviously it's just a picture. But this is kind of how one would be structured. And I thought rather than trying to explain neural networks as a big topic, it might be better to start with what is the individual pieces and then talk about how they work together. So that's what we're going to do. And I got this great analogy when I was doing the research for this talk that someone came up with, and I wish I could remember who it was because it was a really good idea. But he compared logic neurons in a neural network to logic gates, right? So you get a logic gate, this is an AND gate, it takes 3 inputs, and it gives you an output, right? If all of them are 1, then it outputs a 1. Otherwise, it outputs a 0. Here is an AND gate with actual numbers. So here we put in the 2 zeros and a 1, and it's not, x1 and x2 and x3 are not all true, so we get a false out. That's pretty easy. We all know this stuff. Neural networks are kind of the same thing, except they're circles. That's a joke. So here we're putting in 3 values, x1, 2, and 3, and we get y out. And then we've got this black box that does something. And but the key difference here is that instead of putting in 1s and 0s, you can put in non-binary numbers. You can put in floats. You can put in floating point numbers. And so in this example, we're putting in 4.2. Of course, we have to have a 42 somewhere in here. 2.1, 1.3, and we somehow magically get a 3 out. We don't know why, but that's what this particular neuron does. And so to understand what it's doing, we need to look inside of that neuron. And so here we've got sort of all the pieces inside of an individual neuron in a neural network. We've got our 3 inputs, x1 and 2 and 3. And then there's these weights, w1, 2, and 3. And they make the inputs more important. We've got a bias, which influences the output of that neuron. We've got this f of x, which is an activation function, which is actually misnamed. They're not really activation functions. They're more like translation functions. They just modify the output. They used to be activation functions, and I'll talk about that in a bit. But it goes to that function, then it spits out a value. And so breaking it down a little bit, here's our inputs. These are just the values coming into the neuron. If the layer before this neuron has 128 neurons, then this is going to have 128 inputs. That's just the values coming in. We've got the weights on those values. And so they make a particular value coming into a neuron more or less important. And it does that by multiplying them together. So you take x1 times w1, x2 times w2, and then you add them all together. And the bias makes the sum of all those inputs more or less important. So it kind of makes the output of the neuron bigger or smaller. Now, that's exactly what it does, actually. It adds to or subtracts from it. And so far what we have here is a pretty basic function. This is just basic arithmetic that these neurons are doing internally. x1 times w1 plus x2 times w2 plus x3 times w3 plus the bias. So input times weight plus input times weight plus input times weight. Or if you're a little more math oriented and like using that sigma, then you can represent it this way. The sum of the inputs times the weights plus the bias. That's what the neuron is doing up to this point. The output of this will be then rammed into the activation function, which I couldn't think of anything better to say than it adjusts the output of the neuron. It's kind of uninspired, but it sort of filters it out. Originally, it did activate the neuron. So here's one activation function. It's the step function. And in the very first neural network, which was I think back in the 60s, like in the late 60s, they built the most basic neuron called a perceptron. And a perceptron took all these inputs, multiplied them with the weights, added the bias, and then would output either a 1 or a 0. The idea was either it activated, it fired the neuron, or it didn't. And that was great. I mean, it let you solve some basic problems. But it had sort of a fundamental problem baked into it as well, which was this. As you calculate what those weights are supposed to be and what that bias is supposed to be, which is not a thing I'm going to get into because it involves calculus, and honestly, I don't know calculus well enough to talk about it. But we use a technique called back propagation to figure out those weights, and it's using gradient descent. And those are words that I can say. You'd slowly adjust those weights and those biases, and then all of a sudden it would flip. And then it would do the opposite thing. And so it sort of made it hard to train your networks. And so someone said, this isn't really working that well. This is why they're called activation functions, because the original one activated that neuron, and then they went on, and then they didn't activate the neuron, they just sort of adjusted the output. So to address that problem, people started using a sigmoid function, which is also a word that I can say. Basically, it creates this S-shaped curve, which is why it's called a sigmoid function. And instead of giving you 0 or 1, it smoothed out those results. And that improved the neural network. But it also ran into some problems where you couldn't push it high enough sometimes. So sometimes you needed a value to go further. And adding to that weight, that multiplier just wouldn't, you couldn't push it above 1. You couldn't make things more important. Some people played around with using a hyperbolic tangent because it's basically a sigmoid with a negative value. It's just a taller version of sigmoid. But it really kind of had the same limitations. And negative numbers get a little wonky when they're being output by neurons anyhow, because as soon as you start multiplying with negative numbers, it starts inverting things, and that propagates out in sort of weird ways. And so someone said, well, let's just use a linear function. And this isn't even a function at all. Let's just spit out the value. Right? Return x. That's what this does. And that sort of works, but the problem is that you couldn't do deep networks with it, because I'm told, mathematically, when you have several layers, if all your functions, all your activation functions are linear, it's the same thing as collapsing them down into one layer. And so it actually doesn't buy you anything to do deep learning with a linear function. And again, these numbers can get really negative and it's kind of wonky, but they can get really high and positive too. And so the more important a number is, the more you could up it. And so that aspect was good. And that led to probably the most common activation function in machine learning, in deep learning, I should say, is the rectified linear units, which I've always thought was a very, very weighty term for the max function. Because really all you're doing here is saying, if it's 0 or less, it's 0. Otherwise, it's what it is. It's max 0 comma value. It's not complicated, right? But no, it's rectified linear units, which we'll call relative. But that's what it does. And this seems to work really well. And it's one of those things where when you start asking why questions, they don't get answered very well about this kind of stuff. Because one of the things that happens with neural networks is they get big. And so you've got all these connections and you can't hold them in your head. Our brains just aren't big enough. So lots of times we'll get trained a neural network to do something and we don't exactly know why it does it. Like we can analyze each individual piece and see what's happening, but to analyze the whole is just too much work because there's so many permutations. And so when you read about why ReLU is effective, it's because people did things like, well, we tried it and it was. And that's, that's what, these PhD theses will say. They'll say, well, we did an experiment and it showed that ReLU works better. And so they're approaching it from an experimental point of view, less of a, here's the underlying math that explains why this is better. Now, there may be some really smart person out there that has done that, I don't know, but all the stuff I read always sort of had that feel to it. It's like, well, we're trying things and this seems to work better. Which actually, as a not terribly mathy person, as someone who's been a developer for a long time, gave me enormous hope. Like, maybe I could do this. And so rel is what we're going to use for all the stuff here. And it seems to be the most popular function, activation function that people are using in machine learning. I'm sure there are reasons to use the other ones. I don't know what they are. I'll go back to the I'm not a data scientist thing. So then once you've done all that, you've multiplied your inputs times your weights, you've added your bias, you've run it through an activation function, then you get a number. That's your output. And that's what a neuron does. What I think is really neat about this is that aside from the activation function, although if you're using ReLU, this is probably true as well, it's all just arithmetic. Right? The way you calculate what a neuron does is not that complicated. It's just multiplication, addition, and then a function. This is very approachable as a developer. I can get my head around what that means. Figuring out those weights, like I said before, is tricky. That's hard. And I don't know a lot about how that works. What I know is that I can set up my neural network in Keras, and I can call the fit function, and then it does it for me. And as a developer, that makes me happy, and it's sufficient. Now, if I was going to train a neural network to find out whether someone had cancer or not, I might want to get a data scientist to help me out, right? But if I'm, say, building a neural network to recognize handwritten digits or handwritten runes, we're good. I mean, it's you know, there's some things that require that thorough and deep understanding you can get from a data scientist, and there's some things that we as developers can do that don't require, you know, the stakes aren't as high, or the stakes aren't as high, right? Some other thing, right? But a lot of times the stakes aren't as high, or it's just not that complicated of a problem. It's not super, doesn't have a ton of variables, and so it's something that you can get your head around a little better, or it's a domain we're really familiar with, and so we can be effective there. So here's that neural, sort of that neural network idea. Now that we know how a neuron works, what you have here is just arrays of these neurons. And so like you've got your input neurons here. Usually they don't have weights and biases. Usually they're just pegged at a number. And sometimes they don't even have activation functions. They're really just the inputs. Hey, you know, the first value, I've got 3 input values here. You know, if this was like trying to determine whether you should sell your house or not, one of these inputs might be the market value. One of these inputs might be how much you owe on the house, and one of these might be you know, how good your credit is, your credit score maybe. And then it would spit out, you know, Y1 would be you should buy, you should sell. Y2 could be you shouldn't sell, right? But this is you're shoving numbers in here. They all calculate here. So all these neurons through here. The input of X goes to every single one in this middle tier, in this layer right here. And then over here, every single one of those neurons connects to every single one of those neurons. And so those numbers just propagate through. But under the covers, they're recalculating, kind of like a spreadsheet when you type in a new value and everything recalculates on you, or like a binary adder when it goes through and, you know, all the things cascade to create those values. It all sort of recalculates, it sort of trickles through it, and then spits out your value, which is actually kind of amazing. Here's just another way of representing that. I've sort of covered this material. Hey, we put in all our inputs, all of our features, goes through one or more hidden layers, goes to an output layer, and we get a value for values. And so this is a basic neural network. They call it a fully connected neural network because all the layers are fully connected to every layer after it. But it turns out that these are really bad at image processing. It's bad at recognizing runes. And the reason is because, I mean, you can imagine it, right? You got your image, 24 pixel by 24 pixel, you know, 2-dimensional array, and it's got a value for each, you know, how gray is this pixel, right? For a value from 0 to 255. And so you're like, well, I'll just take 24 times 24, which gives me whatever that comes to. And I'll just have that many input neurons. And then have a look, have a guess, have a try and train it. The problem is that when I write this Bjork and hand it in, sometimes it might be taller or skinnier. It might be fat. It might be to the left. It might be to the right. It might be towards the top, or it might be, you know, in the top left corner. They move around, but it's still the letter. It's still the rune Bjork. And so what the neural network has to do is it needs to learn to recognize that shape in lots of different places. And so it basically memorizes what it looks like when it's here, and what it looks like when it's here, what it looks like when it's in the middle, and what it looks like when it's tall and skinny, and what it looks like when it's short and fat. And that requires lots and lots of neurons to sort of encode all that information, to the point where it's actually not cost effective, it's not practical, it doesn't scale. So what are we going to do? Well, fortunately, we have convolutional neural networks to the rescue. And so what they do is they use a series of convolutions and neural networks to solve the problem. So thanks for coming. I've thrown out all the buzzwords. Are we done here yet? Yeah. What that means is, I'll get into here in greater depth, but if we look at here at this image, right, this is representing a 5 pixel by 5 pixel image. Those blue squares there. And we create a series of filters, which are the red ones there, that are saying, look through every pan and scan across this image and say, does it match this pattern? Does it match this pattern? Does it match this pattern? And that creates maps of whether it matched the pattern or not, which are these green ones right here. And then the purple ones are a pooling technique that we can use to help concentrate that data. And then we feed the results of that pooling into a standard neural network. We flatten it out, and then we just run it as a classification problem. I know this looks more like the deck plans of a starship or something. It has vaguely like a spaceship kind of. All of a sudden, I want to watch Firefly. I haven't watched it forever. So here it is. You know, we're taking a tier. We'll do convolution and pooling, and we can do multiple convolutions and multiple pooling. So we can go through that process a couple times. Eventually, we'll flatten it out, shove it to a fully connected layer, which will go to an output layer, which will say that's tier. Here's a better way of seeing that. So here's our input image. We got the rune here, Mather. You know, the best thing about having done this talk is I've learned the names of all the runes. I'm sure that'll be useful someday. But so we've got this input layer, this is just an image here, and I'm just using absolute pixels, so either there's a pixel there or there isn't, to express the idea. And then we've got these filters here. So like this filter here looks for 3 pixels top to bottom, down the middle. And it'll pan, it'll go across that input 1 pixel at a time, 3 pixels high. We're gonna go over 1, over 1, over 1, and saying, does this match the pattern or not? And you can see that in the case of the straight up and down line filter, that we've got 2 matches to that pattern, and so we shove it into that green output. And it says, hey, I found this pattern in these 2 places. The same thing with the plus sign there and the 2 diagonals. It's looking for places in that image where it finds that pattern and then marks it on the output. So this means that if I have a rune and it's shifted to the side, I can still recognize all the parts. And I did a cool animation to kind of show how this works, way better than my explanation did. So we're going across this rune, we're scanning across it, trying to find 3 characters up and down and nothing on the sides. Or 3 pixels. And so we got one coming up here real soon. So right there, it found one. It matched the filter. Right there, it matched the filter. And so we got 2 outputs saying, hey, I found that line in 2 places in this image. And these filters are actually done through the back propagation technique. So you don't like create these filters and say, oh, these are the 10 shapes I know I need to recognize in this thing. It's part of the training process. So when you build this network, it will find the patterns for you. And so it'll look at the image and say, oh, I found these sort of shapes, and you'll get different filters that learn to recognize different shapes. But that was a simplification, because actually we're using numbers. So in this particular case, I've got black represented as the number 1, and white represented as number 0, and then something, any value in between fractions representing shades of gray. I realize this is backwards. 255 is white, 0 is black. But it doesn't affect how the network functions. It still works. And so you've got your input is really the value of all those pixels in a two-dimensional array. And your filter, it's also numbers that are, you do math against the array to say, does this match or not? And there's actually even, you notice that little -1 there at the bottom, right there? That is a bias that comes in as well for that filter. And then the output in green here has, in this case you can see it's sort of matched, right? So we got a 1, we got a couple 2s here because it matched really well. We got a 1 here because it kind of matched. And the way it's doing this is the same thing that we're doing with all the other neurons. So we are taking the blue grid is your x's, it's your input. The filter is your weights. And so we're taking, for example, to figure out the top left corner in the output, we take the top left corner, top 3 by 3 area, and we multiply the weights times the values. Now in this particular case, we've got, up in here, we've got all zeros and a 1, right? So everything in our filter is going to be 0 except for the bottom right, which is going to give us 1 times -1, which is going to be -1. So that's, you've got all zeros and -1, so we have a total of -1. So we've multiplied and summed. We add our bias, which is -1, so that gives us a -2. And then we run it through the ReLU activation function, or the max, which says, well, -2 is less than 0, so it's 0. And so we put a 0 in the top left corner. And we do that across the entire image. And it gives us a map of where it found things that match this image, match this shape the filter is looking for. And it can give us, it's like, yeah, this one really, really matched, and this one kind of matched. And so, it gives us some, it's not as black and white as the pixels would suggest. And so we end up with this map. Once we have that map, which is sort of it becomes a map of, hey, I found this symbol in all these places, and then I found this symbol in all these other places. And you can run these through a second time. So these outputs can be run through another convolution layer and saying, so now instead of looking for 3 pixels top to bottom, you're now looking for a pattern of diagonal, diagonal, pixels, pixels. And it says, oh, when I find that pattern, it matches that. So it's sort of creating a hierarchy of pattern matching. So it's looking for the pieces, and then it's looking for the pieces assembled, and it's looking for the assembly of those pieces, which is actually kind of amazing. And it's kind of how we see. We can look at a letter B and we can see it in all sorts of contexts. This is what this is trying to do as well. Pooling is a way of sort of concentrating our output. So what you do is you take, in this particular example, a 3 by 3, each 3 by 3 section. You say, is there a thing there or not? Yeah? Okay. Then we found it. Otherwise, we didn't. And this sort of gets rid of our white space and gets rid of any, it keeps the network from fixating on, like if you've got like a little, you're drawing a character and you go to the right and left, it's got a little jog in it. It can sort of filter out those things and gloss them over so that it, a little jitter in your handwriting doesn't throw the thing off, or in your training data. It's a way of, really, it helps reduce overfitting. So it doesn't memorize the exact tracing of how you drew it. And so pooling is, here it is with fancy animation. Again, we're panning and scanning, but we're doing each chunk, and we're just saying, hey, is there a thing there or not? And again, we're actually using numbers. And so with pooling, what we're doing here really is we're looking at the top left 3 by 3 and saying, what's the biggest number here? And we look at the bottom. If we look at the bottom middle, right there, we'll look at that 3 by 3 grid. And we'll say, what's the biggest number? Well, the biggest number is 2. So that gets shoved in there. And so it kind of helps trim off the edges and simplify the thing we're looking at, which is why it helps with overfitting. Everyone tracking so far? I didn't hear a resounding yes. I'm not sure. What about the internet? Is the internet tracking? That's what the internet's for, tracking. That was a really cynical thing to say. So the pooling then helps with this. So then you can take this output, you can pool it, and then you can run those pooled outputs through more convolutions, and you can construct these in lots of different ways. Once you've got your final pooled output, or not pooled, you don't have to pool if you don't want to, just it helps. Then you flatten it out. And that's just take, in this case, we've got 3 outputs here, where we've got 3 pooled outputs, which gives us 12 neurons. And so we just take those 12 values and shove them into 12 flat neurons, and then hook it up to a regular old neural network. And then it can, these basically represent the, hey, I found these things in these places. What letter is this? And then the regular neural network can say, well, if you find these things in these places in relationship to each other, then it's Bjork, or it's Mather, or whatever the rune is. So, time for a fun fact. Harald Bluetooth was a Danish king who joined several tribes together. And so when they were coming up with the Bluetooth protocol, they gave it the code name Bluetooth because he was uniting the tribes, and so it was bringing your little devices in your hands and your computers and your phones all together. And so they named the Bluetooth protocol after Harald Bluetooth as a code name. And then they were going to give it a real name, and they couldn't come up with a good real name, and so Bluetooth became the real name. And so the logo is actually the rune Haggle for Harald on the left, and Bjork for Bluetooth laid over top of each other. So we're going to try entering that into the detector and see what it thinks it is. So the tool I chose to use to build my convolutional neural network was Keras. And the reason I chose Keras was because it was a layer of abstraction on top of other more complicated to use, more difficult to use tools. Keras lets you say, I want a neural network, and I want the input layer to be this many neurons, and then I want the next layer to be this many neurons, and I want it to have this activation function. You just specify all the stuff. And so it's sort of like a domain-specific language for building neural networks. And so it helps you think in terms of neural networks as opposed to thinking in terms of the math inside of neural networks. And it sits on top of Microsoft's Cognitive Toolkit, CNTK. It can sit on top of Theano, and it can sit on top of TensorFlow, which are lower level tools for doing this. I chose to use Theano. It's probably not what I would choose if I was building a production application, honestly. Theano is open source, completely open source, but it's also done. People have stopped working on it. And a lot of people are using TensorFlow, or if you're in the Microsoft space, everyone tends to like the CNTK tools. So that tends to be the 2 tools that are more popular right now. There are other tools to do this kind of stuff that I'm less familiar with. Keras doesn't sit on top of them. I'm using Theano because it's open source. But again, like I said, because it's frozen, sunset, I don't know what the good word for it is. No one's maintaining it anymore. I wouldn't build anything for production on it. But it's perfectly fine for a demo. And so Keras is just this layer on top of it, makes it easier to use. It lets you write code that looks like this. This is Python code. You can tell because of the indents. Sorry, it was a terrible joke. It's like the thing everyone hates about Python is the white space showing scoping. I actually kind of like it myself, but a lot of people dislike that. But anyhow, so right here we've created, this is actually the code from building this network for the deep learning like a Viking. You create a model, and the model is called a sequential. And I think it's called a sequential because you're sequentially adding layers to it. And there's another type of model, but I don't remember what it is. I've only used the sequential. It's pretty straightforward. And then we add a conv2D layer to it. It's a 2-dimensional convolutional network layer, meaning I got, like a picture. And so I want to add a convolutional layer to it. I want to have 48 filters. So those little filters that we had to recognize things, I want 48 of them because I think that's a good number. The filter should be 3 pixels by 3 pixels. You can make them any size you want. The activation function will be relu, and the shape of my input is 24 by 24, and it's 1 pixel deep, which is a little odd. Why am I doing a 3-dimensional array here? But and that's because Keras is assuming that if you're doing convolutional neural networks 2-dimensionally, that you could be looking at color images. And so there's the extra dimensions for RG and B, red, blue. That's the reason it's a 3-dimensional array. So I create this, so this is make that first layer convolutions. And then I've got a pooling, and I want my pool size to be 2 by 2. So go every 2 by 2 section there, take the biggest number and drop it, and keep that one and drop the rest. And then I put another 2-dimensional convolutional layer in. Same size of convolutions, half as many kernels or filters. They're sometimes called kernels as well. Another pooling layer, and I flatten it out, and then I take that flattened input and shove them into a 128 neural network, fully connected layer. And again, that's using ReLU. And then I have, as my output layer, 16 neurons using softmax. Excuse me. Pizza's salty. And so I've got 16 outputs because there are 16 runes. And so each rune gets an output neuron. And they'll each get a numeric output. And what softmax does is it says, take all the numeric outputs we have and make them add up to 100%. So scale them down so that it can basically express it as a percentage. So you get a number from 1 to 0 as the output of each of those. And so that means that your output's going to say 0.753, it's this rune, and 0.032, it's this other rune. And give you all those numbers, and you just take the biggest one. And so you just look at all the outputs and take the biggest one. And it's kind of nice because if you look, now the software I wrote doesn't look at this, but if you were to look at that value, you could get an idea of how sure the output was. Like if the winning one was 0.503, and then the next one was 0.497, then that gives you an idea of how sure it was. Or if they're all like 0.3, if the one that wins is like 0.3, it's only 30%, but the other ones are smaller. So that's useful information for output. I didn't do that in this one. But anyhow, that's what softmax does. In essence, turns it into a percentage. Then I call model.compile. And that compiles all this information and it gives it a loss function, which is categorical cross entropy. I don't know exactly what the cross entropy does, but I know that this is the one that every example I looked at that was doing classification was using this because of the categorical aspect of it. Using the atom optimizer, again, I'm really just kind of relying on sample code. There are other optimizers. And a lot of how I got all these numbers for this neural network was not that I was smart and figured out what the numbers were. I put some numbers in and measured the accuracy of the network and said, well, that sucks. And then I put in different numbers. And I'm like, that sucks less, or that sucks more. And so I experimented. And then for my metric is accuracy. So this is how accurate the model is. Once I've compiled that model, then I can actually train it by calling fit. And I pass in my training data. Xtrain is all the images. Ytrain is all the labels for those images. So the images being that array, that 2-dimensional array of bytes that represents the actual image. Y being this image is this rune. It's the label. It's the thing we want to predict. We give it a batch size of 32, which means it runs 32 runes through it, calculates, runs 32, calculates, so it's doing 32 at a time as it does the back propagation until it's out of data. We'll go through that process 20 times. So epochs, so go through our entire data set 20 times. And verbose of 1 means tell me all about it. Let's see this actual code work. How am I doing on time? I think I'm doing fine. Good. So, I took the demo and turned it into runes. And again, good D&D character named Tima. Okay, so let's see what we got here. So I will add, if you guys want to play around with this, do I have the thing running? No, I don't. So I'm going to show off the tool, and then I'm going to show how it works. So let's go into here. I'm using ./bin/bin/activate. That will set up my Python environment. And then I got this shell script which kicks off Flask. And if you want to look at run.sh, all it does is set a couple of variables, run Flask. Flask is a Python library that's kind of like Express is in Node. It's a basic web server kind of thing. I've used it to serve up all the HTML files and the JavaScript files, and also using it to provide endpoints that we can use to do the machine learning. So it looks like it's up. It's giving me warnings saying I should update something, which I'm going to blithely ignore. And then here on localhost 5000, we reload this page and embiggen it. There we go. Did it reload? Yeah. So this is the app. So the big problem I had with this was there wasn't any data sets that had runes in them. And so I had to create one. And so what I did was whenever you load this page, it gives you a random rune to draw. Like if I reload it, you'll see it changes. And if I draw that rune, this is using Canvas, and hit save, clear it out and give me another one to draw. And all this is doing is saving them on the file system. It's making a call to Flask, which saves it onto the hard drive. And then I use those runes to train my model. And I actually committed them all in the GitHub repository so that you do not have to enter them, because this took me a couple hours to get about 500 of them. So I just saved a couple. If we go out and look at on the hard drive here, it is in code. You can see that I got a bunch of GUID.json files. That is the data. So if we look in one of them, you can see that it's just a JSON file. It's got the name of the rune, and it's got data, and then it's just a two-dimensional array of what was in that location. That's how the save function works. And it's also worth noting here that it looks like I'm drawing a really big letter here, but I'm scaling it down to a 24 pixel by 24 pixel image. So if I try to draw something really small like this, that won't work because it'll just turn into a pixel. And so so this input doesn't have the resolution you think it does. But if I go ahead and enter a rune, it should detect it. And so pick a rune, any rune. Wreath. Okay. The first detect is really slow. Hooray! Pick another rune.
Ass.
We'll do soul and then ass. See how after it loads the first one, it gets pretty quick. And then ass. This rune looks like ass. Oh no, I said a bad word on the internet. So obviously it knows how to detect ass. So. And that's as far as we're going to take that joke. We'll do thurs here. And if you guys want to play with this, if you have laptops, because this won't work on a phone, I tried, you can actually go to guyroyce.com/Viking, and it will take you to a deployed instance of this application that I have running out on Amazon. And then you can go ahead and play with it yourself if you like. I'm going to turn that off tomorrow, so if you want to play with it tonight. But again, all this code's on GitHub, and there's instructions on how to get it running. So if you want to play with it that way as well. But yeah, so I did this with about 500 runes. It's actually pretty cool, right? So let's go ahead and build the model, right? So I've got an existing model that's built. If we look in the model directory here, there's this futharkmodel.h5 and this futharkmodel.js. Well, those are the saved model files. And if I call this buildModel.py function right here, or if I run that, it's going to, what it does is it looks at that data folder, loads up all those JSON files, and I'm in the wrong folder. There we go. There we go. So see, it's using Found background. It just loaded all those runes in. It's building the model, which takes a few moments, but here, now we're going through the epochs. You see the accuracy is going up. And we ended up with an accuracy of 92%, which probably means that this is overfit to my handwriting. So this detector is really good at recognizing my handwriting, but other people have not had as much luck, but anyhow. So that gives us new model files. And so if I relaunch the app, waiting for localhost because it's because I restarted it. Come on, you can do it. Oh, the joy of doing live demos. Yeah, there it went. Okay. So now if I go ahead and say, let's do a logger. I could use a logger. Now it's slow because it's loading up that model the first time and it detects logger. So you see that the model built in like a minute maybe, tops, less than a minute. And this model is able to detect these things, which honestly kind of amazed me when I did this. I'm like, this is going to take too long. And I got it working. I'm like, wow, this is fast. I can actually do this at a talk. It was great. So let's take a look at how this thing works. So this is the JavaScript portion of the talk. So I used that fancy library Vanilla.js. I don't know if anyone's familiar with it. Ever use Vanilla.js? I like to use the downloaded gzip version because I like having a couple extra bytes in my file. So I've just got this basic HTML page here with some CSS. It's just got some tag things on it. What there really is I've got an HTML5 canvas here, and then I've got a hidden one that scales it down. And so that's how I'm doing the scaling. It was a lot of fiddling to try and get that to work. I've got these little runic detectors here, or displayers that show the rune, just displays a rune. I've got the little footer here. I love that these are actually Unicode characters, or they have a code point, and so I can just put in UTF-8 for the runes. But there's nothing much here. I'm just crudely bringing in all my script files, and then I've got here I start up the app here. So we got one line of JavaScript in here which instantiates the app class. We go and look at that app class. We see that it's got a constructor which adds an event listener for on-document load. When it loads, it creates a view controller. The view controller, when it constructs, creates a model, the Runic model. Creates 3 buttons. I wrote this little helper button class that just gives me an event for clicking them. And this is the ID in the HTML for those buttons. There's the save, clear, and detect buttons. I've got a rune displayer, which is that little box that shows the rune, the UTF-8 rune. One is the rune that you're going to draw, which is the one on the left, and then the detected rune is the one on the right, but they're the same code, so I kind of treated them like widgets. I've got the Runic Canvas, which is the combination of the drawing canvas where I'm drawing, you see me drawing, and the one where I scale it, which is hidden. And I've got my event handlers for when I click the button, do a thing. And then I select a random rune from the model and set it on the rune to draw. So this is sort of setting things up. When I click save, I select from that runic displayer the rune to draw. I get the rune out of there. I fetch the image out of the canvas. Once I'm done fetching that, then I save it to the model. I call the model.save, passing in the name of the rune and the image data, and then I clear things out and I pick another rune. When clear is clicked, I just clear it, and when detect's clicked, I again fetch that image data from the canvas, and then I go out and call detect on the model, passing in the image data, and then that comes back with a response of what the rune is, and I set that on the screen. This is the sort of the whole the view control process. This is the main flow of the application. If we look at the model, the model's got the Runic model has an adapter and has the runes object. The runes object was just a convenient place to put this data structure and a couple of helper functions to go from runes to names and names to runes and back and forth. But the main thing here is we got save and detect, and they go ahead and call a method on the adapter, which is the thing that actually makes REST calls using fetch. And this data coming out from that Runic Canvas is just that JSON data that we saw in that file earlier. And so we do an HTTP post to save it, and Flask picks it up. And if we go to do detect, we call detect, we do an HTTP post, hand it to Flask again, and it responds back with the rune that we got, that it detected. And then I'm not going to go into the drawing canvas because it's a little tedious, and quite honestly, I'm not super proud of the code. But it's out there on GitHub, and you can check it out. It was just a little fiddly to get it to work because you've got like the drawing canvas is basically has to track a mouse click, a mouse down event, and then the mouse up event, or the mouse move event, and then constantly draw lines every single time a mouse, getting the location of the mouse as you move it. Because you can't just say where you're at, where you're at. You end up with just a series of dots, and so you have to sort of say, the last time you clicked, you told me I was being moved, I was here, now I'm here, so draw a line over that short distance, and then draw a line over this short distance. So you're drawing lots of little segments, and so this is actually a little fiddly, and so you have to keep track of whether we're drawing or not. And then when the mouse comes up, then we turn the drawing to false, so that we then stop looking at the mouse move events. And so it's just a little. I mean, it's nothing horrible. It's just a little tricky. The canvas we're drawing on is 240 pixels by 240 pixels. The scaled canvas here is 24 pixels by 24 pixels, and so when we get the image data, it compresses it down, of course, automatically, which is really handy. So, yeah, that's the JavaScript, and it's all sitting here in this static folder, being served up by Flask. So, how many here have messed with Flask at all in Python? A handful of you? Okay. So here's my, for lack of a better term, probably a hack with Flask to serve up the HTML, CSS, and JavaScript files. If you go to the root folder, bring static/index.html up. If you bring up anything else, it brings up static/ whatever the other thing is. So basically, look in static for anything you don't recognize. And if the file's there, serve it up, and if it's not, serve it with 404. But most importantly here, we're registering this blueprint for runes. And in here, we've created two endpoints. This blueprint is at the /rune endpoint, and there's the /save and the /detect. And so the save generates a random file name. Now, I guess uses a UID to create a file name, and then takes the request JSON and turns it into the file format we want. I got a class that sort of wraps up that saving mechanism. I save it and save the file name. Yay, we've got a JSON file on the hard drive. That's all it's really doing. Detect is actually doing something very similar, but one of the things we had to do was we have to take the labels. This is 0, out of the neural network that we build to detect these runes, we get the numbers 0 through 15. And we want the names of the runes. And so this Futhark labels encapsulates the tools used to convert things from numbers to labels and labels to numbers. And so we instantiate that. And all it does is it takes the names of the runes, alphabetizes them, and says, you know, AR is 0, R is 0, and AS is 1, and whatever the other comes after that. All I can remember is that. We got a model which encapsulates the model we built, and we load that. And then it's just a matter of taking that JSON, formatting it in a way that can be used by the model, calling predict on the model, passing in that Rune data, taking the prediction, decoding it, and the decoding wants an array. So we shove it into an array. And then it returns an array, so when we return the message, we have to say, give me the first element of that array. So that's all we're doing here. The really interesting thing here is in the model itself. If you look at labels, it's really nothing fancy. It's just using this sklearn label encoder to encode and decode. But in the model, we've got a little bit more going on here. So in the model, we pass in X and Y. X being all of our features, that'd be the images. Y being an array of all the labels. So we got 500 runes, so we're passing in 500 images in an array, and we're passing in 500 labels in an array, and they line up, they match up. The first thing we do is we split those into test and train sets. And so we pull back 20% of that data so that we can test our neural network, get a measurement of its accuracy. And then we use the other 80% to train it. And this is just a thing from Scikit-learn, which does that for you. Then we take these types, and these are NumPy arrays. And we say, no, I know they're integers, make them floats. And then we divide them by 255 so that we get a value from 0 to 1, which works better with neural networks. We take our labels, and convert them to categories. And then this is the code that was in the slide. So this builds our model. And then we save that model off to a member variable, and we'll return an evaluation of how that model scored at the end. Saving the model is just is a two-part process. There's the structure that is saved as a JSON file. If you go and look at the JSON file for the model, it'll have the name of the activation function. It'll say how many nodes are in it, that kind of stuff. In the load, the other file is the H5 file, which is a binary file that contains all the weights and biases in that neural network. And so you need to load both of those together for the model to be loaded or saved. And load just does the opposite. And then predict just uses that underlying Keras model, calls predict classes, and then passes in your data. And it is expecting an array of things to predict on, not just a single item. And so we have to take our input, which is three-dimensional because it's got a depth, a height, and a width, and say, well, we've got one of them. So we need to make it a four-dimensional array, and then when it's done, return the 0th item. So when we're doing a prediction, we're kind of arraying it and de-arraying it, which I'm sure we've all done that before. And so that's the way this code works internally. And you can totally, this is all out on GitHub. You can pull it down and play with it. Here's the Rune file, which is just managing JSON and taking JSON and turning it into NumPy arrays, and taking NumPy and turning it into JSON. It's doing that sort of work. And that's pretty much all the code. Let's see. Let's get back to the slides. Any questions so far?
I don't think it doesn't recognize it.
It gives it your best. It gives it a best guess. So yeah, let's do that actually. That was the thing I wanted to do. Let's go ahead and give it the Bluetooth logo. If I can write the Bluetooth logo. There we go. That's sort of the Bluetooth logo. I can do better. It's actually really hard to do on a trackpad. Okay, hit detect. It thinks it's Bjork, which isn't terribly surprising because that's probably more of what's there. So it's got to guess something, and so it guesses something. So if it doesn't recognize it, it's going to say, "I think it's this." There's not a category for it. I don't know. I suppose you could do that actually. Yeah. Okay. So here's some resources that I gathered when I was putting together this talk. Of course, there's a link to Keras, Keras.io, which is probably the most important thing of all the things on this resource here, because it's the actual tooling that I use to build it. Microsoft CNTK, TensorFlow, and Theano are all out there. You can pick whichever one you want to use. Here's a link to Flask, a link to Vanilla.js, because that's useful. If you're curious about the younger Futhark more, there's a link to that. The Neural Network Zoo is really interesting. It's got a bunch of, it's sort of like a classification of all these different types of ways of arranging neurons to build neural networks, different architectures. And they've got, and of course, convolutional neural networks are there, and then your basic fully connected network. But they also got things like recurrent neural networks, which are often used for like generating scripts. You've probably seen those things on Facebook where someone says, "We took an AI and fed a whole bunch of episodes of Family Guy in there, and this is what it said," stuff like that. Yeah.
Actually, I do have a question now. So you said that Keras takes whichever value is highest and says this is what that is. Is there a configuration built into Keras where you can say, all right, let's probabilistically do that gap? So
You're talking about in the case of like pooling, or?
well, I mean, I'm just saying, well, like when you click output right now, it's going to give you your every time. But what if it only gives you your 60% of the time, and 30% to the other one, and then other 30% to here?
So if you give it the same input, you should always get the same output. The thing's completely deterministic. It's very complicated. It's very complex. There's lots of stuff going on in there, but it's 100% deterministic. So if you draw a Bjork and save that image and keep feeding that image into it again and again, it's always going to do the same thing. Now, if you keep redrawing Bjorks, and some of them are a little different, and it recognizes 60% of them, but 30% of them doesn't, then it means you need to provide more data to build a better model, if that makes sense. I don't know if that answers your question or not. Yeah, it's still, I mean, like every computer thing you've ever done in your entire career, it's still garbage in, garbage out. Right? If you've got bad data, you're going to get bad results. Yeah.
Just piggybacking on his question, I would expect that there's some probability for all 16 characters. It would be interesting for that, where 70% Bjork and 20% whatever the H character was.
Yeah.
And then everything else was in the dirt.
Yeah.
I mean, that would be really interesting.
Yeah, you can get that information. My example doesn't do that. I don't, I'd have to figure out how to do that.
Of course, it's deterministic, but you do have
Well,
16 probabilities.
Yeah. Well, and in the case of the Bluetooth logo, it's very possible that it's got a close second.
It might be 60-40.
Yeah, and then zeros for the rest. So yeah, that's totally possible. Yeah, I saw a question back here too. Sorry, is there? All right. Hi. There's a post in the way. I'm sorry. There's a post. I wasn't showing you. Yeah.
If you wanted to have it recognize a room regardless of its rotational orientation, so if it's upside down or diagonal, would you go about that using it for data or
Yeah.
in
Exactly right. Now there comes a point where it stops working, right? Where if you take certain letters and turn them upside down, like if you look at the runes, there's Mather, which is the one that looks like this, right? And the YMCA one, right? But then there's another one, which I don't remember the name of, which is the same thing upside down. And so if you rotate it too far, then a human's not going to know what it is, let alone, it actually is ambiguous. And so that's not good training data. And so, but yeah, that is the thing you do where you can angle them and it can still figure it out. I did not train in the data like that. I drew all my runes nice and neatly. And so when I draw them nice and neatly in a talk, it works. What I really have done with this talk is there's a popular example of this process using the MNIST number data set. And there's 60,000 handwritten digits, 6,000 of each digit. And they train that. They use that to train it to build a model to recognize handwritten numbers. And I said, let's make this runes instead, because that would be more fun. And then I made 500 runes, because I didn't have time to put 60,000 in. And so I don't have the variation in my data set. So it's actually small for what I'm really trying to do. Well, actually, it's the right size for what I'm trying to do, which is just have sort of a fun demo. But if I wanted to do this seriously, I would need a lot of different runes from a lot of different sources and to get better data. So, other questions? Make sure I'm not know what's hiding behind your pillars? Yeah.
I believe there is a Keras JS library. Do you ever have any experience with that? Maybe like browser side?
I have not done anything with any JS version of Keras. There is a JS version of TensorFlow, which I have poked at for like 30 minutes, and that's the extent of it. At the risk of sounding mean towards JavaScript at a JavaScript meetup, the JS for TensorFlow is a toy. It just doesn't have the performance characteristics required to do anything real. A lot of what we're doing with Python behind the scenes is actually calling into C libraries, because even Python doesn't have the horsepower as an interpreted language to really build these neural networks up. And so all the heavy lifting is all done in C++ on GPUs. I'm doing it on C. I'm pretty sure it's happening in C++ on my laptop. I don't think it's using my GPU, but I also have a really small data set, so I can kind of get away with it. So like what I built here could probably work in a browser-based solution because it's not a lot of heavy lifting. But again, those tools tend to be really honestly toys.
Yeah, you want to do smaller things out at the edge anyway, where you likely have less computer power. So in a browser, that's not the place to do big heavy grinding and that type of stuff. There's smaller things that you're learning out fine, but so the JS, if you're using the JS, you would, and thought you were going to try to use it for something big, it would be Node on the server.
It's also worth noting that building a model is way more computationally intensive than using a model.
Yeah.
So you notice how fast the model came back once it spun it up the first time.
Yeah, I remember.
But building that model, we sat there and it took about a minute.
Right, I watched a little bit of like the Google presentation on TensorFlow.js. One of the use cases they had in the browser was to crowdsource training your model. If you had a lot of people going to your website, there's like a potential interesting use case where you can crowdsource that and aggregate it on a server or something like that.
I thought about doing that actually for this because I built a little web app that you could draw runes in. But ultimately, I didn't have a place really to host it effectively for any length of time. And I was a little leery about gathering runes from the general public and not vetting them after the fact. So God knows what someone would have drawn. So there was, yeah.
Yeah, so you mentioned it's running on GPUs. Is it possible to just run it entirely on CPU?
Well, that's what I'm doing on my computer here, actually. Generally, when you build the models, you're using GPUs because it's just, they're designed to crunch lots of numbers, and that's what machine learning is doing.
So can you use your iGPU for that? Because I'm assuming when you...
Yeah, I could use the GPU that's in my MacBook here.
Okay.
Yeah, I could totally do that. It's just configured to do that.
Okay, so you configure it to do that. I'm guessing like it converts it to shader language for GPU to
I
handle it? Like,
I have no idea.
Like, is that just built in?
I didn't experiment with trying to get it to work because I didn't need to for my particular problem. I think it's just a setting in Theano to use your GPU or not, but I'm not sure. I haven't played with it at all. I'm sure it's just some environment variable or some setting that you set in your code, and then all of a sudden it magically use a GPU. But I haven't tried. So. Did I see a hand up over here?
No, I was just going to say that there's an industry standard called CUDA or something like that.
Yeah.
Specifically for NVIDIA GPUs. I think that might be what you're talking about.
Personally, when it comes to machine learning with GPUs, I'm kind of glad Bitcoin's dropped. It means we have more GPUs freed up for doing machine learning. So there's some other links on here too that I use to cut some blog posts and stuff, and an online course that I used to help learn a lot of this material. So you can check those out. That's the link to my GitHub repository with all this code. So if there's a link you want to get a picture of, this is probably the one you want to get a picture of because it links to everything else. So, and we did questions already. Were there any other questions? Oh yeah, I said take a picture of this and then click, click, click. Yeah, no problem. Anyone else? You sure? Okay. The internet is waiting on you. All three of the people watching this in the live stream. There's someone out there raging saying, there's 4, there's 4. Questions? That's me. Again, follow me on Twitter if you want to see what I tweet about. Sometimes it's even about work. Again, my GitHub link there. These are all the images I stole off the internet. And that's Data Robot. So thanks a lot.
Thank you very much. We're going to wrap up. Feel free to grab whatever pizza's on the way out and put it in a doggy bag, plate thing, situation whatsoever. Do not leave me with all this pizza, please. We will start ordering an appropriate amount of food, at another point in time, which we didn't do today. So.